this video, we are going to go over some problem-solving techniques for general chemistry. Step 1 of this multi-step process is to read the problem. What type of problem is it? Underline your unknowns to make sure you really know what you're working with, and also make sure to write the variable name above the number. That way, you'll be able to keep better track of what you're working with. The next step is to write your givens. If variables are involved, make sure to write them down. You'll see here that I wrote 3 different versions, one which is good, one which is medium, and one which is bad. The good one involves writing lambda, the variable, along with its value in SI units. The second one involves the value in SI units, but it does not have lambda. So if I have 10 givens, I'm not going to remember which one that one is if I don't assign a variable to it. And last but not least is just the number with no unit. Imagine if you were taking a test and that's all you had written down. How would anyone know what to do with it? So at the end of the day, it is going to be best to write down your unit along with the variable. In addition to part 2, I also wanted to add that if your units are not initially given in SI units, make sure to convert them before solving your problem. For example, if you are given a length of 300 millimeters, while that is a good length, it's not in SI units. Make sure to first convert the millimeters into its SI equivalent of meters. You can look up a list of SI units on Google, and that should give you a good idea for how to do the conversions. One other thing that I do is I assign the bigger value to the smaller unit. For example, since millimeters are smaller than meters, there are going to be more millimeters that fit in 1 meter. When I do that, I will rewrite my given from L equals 300 millimeters down to L equals 3 times 10 to the minus 1 meters. Now that we are done writing our givens and converting them to SI units, the next thing we need to do is put on our thinking cap and strategize. What are you solving for? Can you make a list of formulas or equations to solve your unknown more readily? If you're stuck on a problem or not sure how to start something, is there something that you're missing? Once you've strategized and figured out what exactly you're solving for, now it is time to solve for that unknown. What I like to do is I like to write my work in a numbered list. That way, it's easier for me to see what I'm working with. Especially if I'm on a test and I'm crunched for time, it's going to be easier to look back at a clean roadmap of what I'm solving for. I always like to start by writing number 1, givens, and then writing that below with subpoints A and B with whatever my givens are. When it's time to solve for the calculations, I'll make a second point, 2, calculations, in which I'll start with the formula that I need, which in this case would be solving for kinetic energy, and I would write down the generic formula first. That way, it's easier on my eyes to know what specifically I'm solving for. Then after that, I will plug in my values that I was given so that I could solve for the unknown. Once I do this, I find that I receive a kinetic energy value of 86.7 joules. One side note is, if you need to conserve significant figures, which in both cases have 2 significant figures, then you would rewrite your kinetic energy value to be 87 joules, as that's the closest to what your final value is. One step I wanted to add on to step 4 is that although I always solve work with SI units, as should you, you may be asked to report your final value in a different unit. If that is the case, solve all your work and all your dimensional analysis and your math with regular base SI units, and at the very end, convert it back over to whatever unit your teacher is asking you to solve for. It's kind of like how, when we start, we may be given an odd unit, we convert it to our SI unit, and then at the very end, we'll convert it back to where it started. Finally, for step 5, I want you to perform a gut check. Did you use your SI units, or did you forget? Did you input your values in your calculator correctly? Remember to use scientific notation? Remember to use degrees or radians whenever needed? Etc. If you forgot to do one of those, chances are your answer will not make sense to you. And that's okay. That's a sign that maybe you did something wrong and that your gut doesn't agree with what you're saying. In that case, just look over your work once more and see what you need to fix. Last but not least, we're going to go over a problem that involves all 5 of the steps that we worked on previously. A CO2 laser with a power output of 65.4 watts, or 1 watt equals 1 joule per second, with a wavelength of 9.40 micrometers, is focused on a surface for 22.8 minutes. A, find the frequency in hertz, which I forgot to say, and B, find the energy output in kilojoules. So first and foremost, let's find some givens. So first, power equals 65.4 watts, which is the same thing as saying 65.4 joules per second. B, lambda equals 9.40 micrometers, which is the same thing as saying 9.40 times 10 to the power of minus 6 meters. And time equals 22.8 minutes, or 1,368 seconds. I'm going to save some space and replace our original lambda and time values with our new ones in SI units. Now for part 2, let's do our calculations. I'm going to let part A be finding frequency, and then part B be for finding the energy output. So for part A, what do? Well, in most chemistry textbooks, you should be told that C equals lambda nu, where C equals the speed of light. The speed of light, C, equals 2.998 times 10 to the power of 8 meters per second. So doing that, we can also isolate nu, or frequency, and rewrite this formula as nu equals C over lambda. When we do that, we can start with this brand new fresh formula and just plug and chug. C is 2.998 times 10 to the power of 8 meters per second. Lambda is 9.40 times 10 to the power of minus 6 meters. The meters cancel, and we're left with inverse seconds. And inverse seconds is the same thing as hertz. So when we do that, we get 3.19 times 10 to the power of 13 hertz. And this is your frequency. For part B, finding the energy output, well, notice this. Energy is usually measured in joules, as that's the SI unit after all. Power is measured in joules per second, and time is measured in seconds. So these can cancel out, leaving us with joules are equal to joules. So now I can say that energy just equals power times time. And in this case, power is 65.4 joules per second, and time is just 1,368 seconds. So we see that the seconds cancel, and that just leaves us with a final value of 89,500 joules. But we're not quite done yet. We need to convert this into kilojoules as the problem asked. So what we can do is use our dimensional analysis as always, put our joules here so they cancel, kilojoules on top because that's what we want, and there are 1,000 joules for every kilojoule. So doing it this way, we're going to get a new value of 89.5 kilojoules. So we see that we pretty easily found what nu and energy is. And with that, that's how you can solve your chemistry problems much more organized, following those 5 pieces of advice. Why don't you give it a try at home and let me know how it worked for you in the comments. I'll be happy to review the comments and make another video of how well those 5 tips worked, and we can always course correct if needed. Thanks so much for getting to this point in the video. Have a good rest of your day, and see you in the next video.